So, right, we ended with factorials dominating exponentials. All right, and now what I want to do is I want to show you some common converging sequences. And I'm going to show you these in the form of limits. And so if you encounter any of these sequences or any variation of these sequences, you're allowed to just cite the limits that we record now, okay? And we've actually proven 2 of them are true. So and these will crop up later as well when we get into series. So these are things you want to make sure you know and that you have down. All right, so the first one is the limit as n goes to infinity of the natural log of n over n. And we can very easily prove using L'Hopital that this thing goes to 0. The second one is that the limit as n goes to infinity of the nth root of n is 1. Now another form that you may see this one written in, oops, this should be going to infinity, is right when we have radicals, we can write them as fractional exponents. So that's the same thing. Those are the same equivalent limits. So we might see them as the nth root of n. You might see it raised to the 1 over n. Right? The next one is actually going to involve an x. I'll show you what that means. So the next one says, well, if you have the limit as n goes to infinity of x to the 1 over n. All right. So rather than having a base of n raised to 1 over itself, we've got just some constant. So x in this example is representing a constant number. You'll rarely see it in the form of x, but this is always true as long as x is positive. So it could be 2 to the 1 over n, right? 4 to the 1 over n. So the next one says, well, if you take some constant number and raise it to the n, and you look at the limit as it goes to infinity, well, we know if that base is bigger than 1, so like 2 or 3, we know that those are exponentials and they're going to blow up to infinity. But if the number that we're raising to n happens to be less than 1, right, or a fraction, and the reason we use absolute value is this particular limit allows for the base to be positive or negative. So it could be negative 1/2 to the n, positive 1/2 to the n. When something's smaller than 1 and you keep multiplying by itself, it just gets smaller and smaller and smaller, so everything's going to end up at 0. All right, and then we have this guy, which we proved in class. So, right, we said this is just going to turn out to be e to the x, and this is true for any value x we pick. The last one, we also just proved at the end of class last week, right? And this is true because we know factorials dominate exponentials. So if we put the factorial in the denominator and the exponential in the numerator, everything will go to 0, and that this is also true for any x. So let's make sure we note here, x is a constant in all of these, not a variable. So let's look at 2 quick examples, and we'll see how what I mean by when you recognize one of these limits, you're allowed to just cite it. You don't have to go through and do all the work that we would normally do. All right, just make sure everybody's caught up. All is copied. And we'll shift this up just a little bit. So if we give you the sequence 1 plus 3 over n raised to the n, you still need to make sure that you understand that you're applying the nth limit test, right, the infinite limit test to test for convergence. So once you set up the limit and you recognize that that's just e cubed, we would then conclude that the sequence a sub n, right, converges to e cubed. So just don't forget, if you tell me a sequence converges, then I need to know what it's converging to. So similarly, right, we have 1/2 quantity all raised to the n. So this is the limit number 4 in our list, which just said if you have x to the n, and as long as that x is less than 1, or the absolute value of it's less than 1, we know that that converges. So the limit as n goes to infinity of 1/2 to the n is 0. So we can just state that it converges to 0. So like that's the minimum amount of work that you would need to show for something like this if you recognize the limits. All right, so are there any questions on this? Because we're about to switch gears and talk about some different theorems. I just make sure everybody's kind of on the same page, because if we're not, we need to clear it up now. All right, good? Okay. So up until now, right, if we want to test something for convergence, we've used limits, right? Then we've seen that there are a lot of well-known and commonly occurring limits we can look at. But sometimes it might just not be possible to take the limit, or the squeeze theorem isn't easy, or, you know, there might be a simpler way. So if a sequence has certain recognizable characteristics, we can just determine it converges using two really useful theorems. So the first thing we need to go over is a little bit of background here. So let's look at the first theorem I want to show you. And that's the absolute value theorem. So always remember, math people aren't really that creative when they name things. So a lot of times the name itself is giving you a big clue what's going on. So if we say absolute value theorem, there's a big chance that we're going to take the absolute value of something. That's just what's going to happen. So if you look at the theorem itself, what we say is, well, if the limit as n goes to infinity of the absolute value of a sequence equals 0, then we know the limit of the original term, oops, no absolute value anymore, also equals 0. So when we're looking at sequences, right, and a lot of times the tell of when you might want to apply this is if you have an alternating negative term, right? You have like -1 to the n times something, when the terms are going to bounce back and forth between negative and positive. We could have an x to the n situation where the value inside of that is negative, and that would create the signs alternating. So what this is saying is if you just look at all the magnitudes of the numbers, if we just take all the positive values of every number, and we see those are trending towards 0, then even though they're bouncing back and forth, those will go to 0 as well. So one of the things that I kind of like to think about this is when, if any of you have ever worked with springs, right, you see that if you map the motion of a spring, so it's just bouncing up and down, right, it oscillates, and we usually use a wave to bounce it out, like a cosine or a sine wave. But in reality, if you attach something to a spring and you pull it, well, the spring eventually stops moving, okay? So, so if you were to graph what that motion looks like, you would see something like this. You would see that the first bounce, you got a little, like, got some distance, and then every subsequent bounce, right, it got less and less and less distance until finally it just stopped. So if you were to graph an alternating series that was trending towards zero, it would look something like this. You would see a positive term, right, and then a negative term, and then another positive term that was probably a little bit less, right, and then another negative term, and positive, negative, positive, negative. And what we're seeing here is the value of these numbers are starting to settle around zero. So what the absolute values theorem does is it takes all these negative terms, right, finds their respective place in the positive territory, and you can see as these dots above the line are trending towards zero, we can see that the negative ones are going to follow the same pattern as well. So that's really what we're just doing here. If we just look at the absolute value, we say it converges absolutely. So let's look at an example of what we mean. And how would you show this? So we definitely know this guy converges. We've looked at it a lot of different ways. All right, one, I can see it's going to converge because of the nth limit test. Right, but that -1 to the n is what's telling me that, oh, it might be a good candidate to apply this theorem. So if I look at the absolute value of this sequence, well, the absolute value of it is just going to turn it into this, because the numerator will only ever be 1 or -1, and the absolute value of both is just 1. So now, if I take the nth limit of the positive terms and I get 0, well then that tells me that the alternating series will also be 0. So if you wanted to actually evaluate the limit of the alternating part, we would have had to use squeeze theorem or something like that to evaluate that limit. We would have squeezed it between 1 over 2 to the n and -1 over 2 to the n. The absolute value theorem just sort of cuts that step out for us. It just says, well, let's just look at the positive terms, and if we get 0, great, then we know the whole thing's 0 and we can move on. Okay? Good? Okay. All right. So the other thing I want to define before we start putting all this stuff together is monotonic. So what is a monotonic sequence? So once again, the clue is in the name. Mono means one, okay? And the short answer for what a monotonic sequence is they are sequences that only move in one direction. So there's two possible ways we can determine something's monotonic. So a sequence is monotonic if its terms are non-decreasing, which I know this is like a little cumbersome way of defining that. So what we mean is the first term is less than the second, is less than the third, so what we're saying here, it's moving in only one direction, and the direction in this case is moving up. These terms are steadily increasing. And its first term is the smallest term in the sequence, and then they just gradually move up from there. So that's what we mean by monotonic. It just gradually moves in one direction, right? A sequence, right, is also monotonic if its terms are non-increasing. So in this case, the first term is the largest term in the sequence, and they just get smaller from there. So in this case, they're still only moving in one direction, but that direction is down. So A sub 1 is the largest term in your sequence in this case. So sometimes you can look at a sequence and you can just tell that it's monotonic. You can list out the first couple of terms and it's blaringly obvious that things are getting bigger, things are getting smaller. Sometimes if you're looking at the definition in terms of n, it's a little ambiguous. So there's a way algebraically you can test to see if something's monotonic. All right, so let's look at a couple of quick examples. So we want to know, are the following sequences monotonic? Okay. So we've looked at this guy before. We know it's bouncing between 2 and 4, and it's definitely not monotonic, right? It's going up and down and up and down and up and down. So it's not moving in one direction. And so this sequence is not monotonic. Right? And sometimes I told you just be really obvious. You can just look at it and tell. All right, well, what about this one? So I could plug in a bunch of values of n, and I could look at the list and I could see, but I'm going to be lazy and I don't want to do that. And there's a way we can generalize, right, and test algebraically if this is monotonic. So really what I want to do is I want to just set up an inequality between any two consecutive arbitrary terms. And if I can just show that in general, they're always growing or always decreasing, I'm done. I can say I have a monotonic sequence. So what we can do is we can say, well, let's pick the nth term, right, and compare it to the nth plus 1 term. Now, I'm going to pretend for a minute that I don't know what's happening here. So that little box I've drawn, there should be a greater than or a less than or equal sign there. I just don't know which one yet, okay? And so if you remember the way algebra works with inequalities, as long as you do not multiply or divide by a negative number, the sign doesn't flip. It just stays intact. You can treat it just like an equal sign. So I'm going to define the nth term, which is easy because it's given right here. And the nth plus 1th term, right, we just plug in an n plus 1 everywhere we had an n. So then what I want to do is I want to try to, and this is what's kind of crazy about these, they're kind of neat. You just algebraically manipulate the equation until you get to a line where it is blaringly obvious which one's greater than or less than. And as soon as you're there, right? So this one we're going to take down a little further. Some of you may see it earlier just to kind of show you what's going to work. Once again, notice here, I'm going to check for positives. Everything I'm dealing with here is positive. N will always be a positive number. There were no negative ones or anything in here. So I know I can just plow through the algebra and I'm probably going to be okay. So the first thing I'm going to do is I'm going to cross multiply these two terms. So on the left, I'm going to have 2 to the n times n plus 2, because I'm just going to go ahead right here and simplify this denominator a little bit. You can see you have 1 plus n plus 1. That's just n plus 2. Then on the right side, I've got 2 times n plus 1 squared. So there's my first n plus 1, and this is the same thing as n plus 1. Then I want to expand out each side. So I'm going to get 2n squared plus 4n on the left, and on the right, I'm going to have 2n squared plus 4n plus 2. Now I can already tell that the right side's bigger than the left side, but just to make a point, just to beat it home, right, I'm allowed to subtract 2n squared from both sides. I can subtract a 4n from both sides, and now I'm left with this. So it is blaringly obvious now that the right side was bigger than the left side, so I know that this is less than or equal to, and since nowhere along the way did I do any math that required me to flip the sign, I can go back and retroactively fill in that inequality sign, and I can see that this sequence is monotonic increasing. Yeah, question.
Question on proof. So you multiplied by n plus 2 to both sides, but you have n plus 1 squared.
Over here, I did not multiply both sides by n plus 2. I cross multiplied. So this denominator was n plus 2, and this denominator was 1 plus n. Yeah. And so this isn't, I mean, I guess technically this is a proof, right? But what I was doing is I was just testing to see, is it monotonic? Because you're going to see in a couple of minutes that when we know a sequence is monotonic and it has an additional feature attached to it, like there's ways we can determine convergence and divergence very quickly. So this is just showing that you can just test any two arbitrary terms. And usually what we do is we compare the nth term to the nth plus 1 term and see what we did. Does everybody understand why I was able to retro fill in those signs, right? So as long as you didn't do anything that flipped the sign, this works to test for monotonic. All right, so the last attribute I want to talk about that can happen with sequences is a bounded sequence. Right? And there's sort of like 3 subsets of what can happen here. It's 3 different ways you can be bounded. So the first one So what we're saying is a sequence is bounded above if there is a real number m that we can find, we actually call it out, such that every single term in the sequence is less than or equal to m for all values of n that you plug in. And then we refer to that number m as the upper bound of a sub n, right? So there's never just one of these. Sometimes, and obviously any number bigger than that number m would also be an upper bound, right? And so sometimes the goal is just to find any number m. Sometimes you want to try to find the smallest number m you can find, but the goal is to just find some real number that we know every term in the sequence is less than. So we know it's bounded above. We can also have a sequence that's bounded below. So similarly, right, we can have a sequence that's bounded below if there's a real number n such that all the terms in the sequence are greater than or equal to that number, right? And then we would call n the lower bound. So we can actually tie these first two criteria back to monotonic sequence. So if a sequence is monotonically decreasing, well, then its first term is the biggest term in the sequence, and that's also could be its upper bound, right? It's just never going to be larger than that value. If a term is monotonically increasing, right, then the first term is the smallest term of the sequence, and it grows from there, and so we know that that first term could be its lower bound, right? Or you could just pick a number just below that to say, well, we know it's bounded below, right? When we talk about bounded, right, so we've talked about, notice here that this says bounded above, bounded below. But if we call a sequence bounded, it's bounded, just generally, if it's bounded both above and below. All right. Where's got this? All right, everybody got this? So let's go back to this guy again. So we already determined that this thing is not monotonic, right? It's bouncing back and forth between two values. However, it is bounded. It's bounded above and it's bounded below. So this is, in fact, a bounded sequence. And we could say, well, its lower bound is 2. Its upper bound is 4. Oops. Right. So how do we tie these two ideas together, right? Well, there has to be some kind of, sorry, my mind's blanking today, guys. I've got medicine in me. But there has to be some kind of advantage to knowing if something's monotonic and it's bounded. So what is a bounded monotonic sequence? So if you recognize that a sequence monotonic and you see that it's bounded, and I don't mean like bounded above or bounded below, I mean straight up bounded, right? So if a sequence A sub n is bounded and monotonic, then it converges. So I actually have a problem on the practice quiz that you just can't really do. It involves some factorials, but the way the factorial is structured, you can't write a formula A sub n to capture the terms. And so, but if you pay attention to the way the terms are going to look when they're structured, you'll see whether it has monotonic, you can tell whether it's bounded or not, and this is another way of showing whether something can converge or not. So you just may not always be able to rely on traditional algebra methods, and this is a really, really useful theorem to know, all right? And so for me, when I was learning this stuff, it would be so frustrating because I wasn't always great at grabbing these theorems in my head, and I would be like, I can see what's happening. I know it converges, or I can see that it diverges, but I couldn't mathematically express it. So understanding these two ideas are pretty useful. So let's look at a couple of sequences that we've looked at before, but now let's kind of look at them in a new way. So let's look at this guy. Is it monotonic? All right, which way is it going, up or down? Down, right? So start at 1, 1/2, 1/3, 1/4, right? It's definitely monotonic. So it's monotonic. And that's why I said sometimes you can just tell by looking at them. And it's monotonic, and we know it's decreasing, right? Is it bounded? So we only have to find at least one M or N, right? So is it bounded below by anything? 0. So there's a big clue right there. If all the terms in your sequence are positive, greater than 0, then it's bounded below by 0. That's just going to be a given. So this thing is bounded below by 0. What's the biggest n can ever, 1 over n can ever be? 1. So it's bounded because it has an upper and lower bound. And it's monotonic, so it converges. Now, we also know this converges because we can apply the nth limit test, and we can say, well, the nth limit goes to 0, it converges to 0. But this is a really simplistic example that you're like, oh, this thing's never, it's always getting smaller, it's bounded below by 0, it's bounded above by 1, so it converges. And like, I don't need to see any other work other than that, right? But if you say something's bounded, you need to tell me what the upper and lower bound is. All right, let's look at one that's maybe not so straightforward. Now, I know from the nth limit test that this guy's going to blow up to infinity. So I know this thing diverges, but what I want to show you is it fails the theorem as well. So I want to show you that this is a known sequence that we know is going to diverge because it's going to blow up to infinity, but I want you to see that it fails this criteria. So first and foremost, let's check to see if it's monotonic, because that's the first thing that has to happen. So we can check for that by comparing the nth term to the nth plus 1 term. So I'm going to pretend I don't know which way this is going, all right? So then, when I cross multiply, on the left, I have n squared. Once again, this turns into n plus 2. On the left side, I have n plus 1 cubed, because it was n plus 1 squared times another n plus 1. When I expand out the left side, get this, and on the right side, and so I can see that these n squared terms cancel, and by comparing the left side to the right side, I think it's pretty obvious that the right side's bigger, okay? So this thing is monotonic, right? So it's monotonic and it's increasing. But is it bounded? Okay? So it's going to be bounded below by 0 because all the terms are going to be positive. So it's definitely got a lower bound. And the fact that it's monotonic increasing, it's at least bounded by its first term, right? So if I put in a 1 in here, I would get 1/2. So it's even, we could even say 1/2 bounds it below as well, right? It'll never be smaller than that, or bigger than that, excuse me. I'm sorry, smaller than that, we're increasing. However, what about its upper bound? Well, it has no upper bound because the limit of the nth term is going to infinity. So this thing is bounded below, but not above. And so this diverges. So I'm trying to show you things where we have other methods to confirm our hypothesis about diverging and converging, because one, I want you to see that there's a bunch of different ways to get there, and two, I'm just trying to confirm this stuff does work. It's just an alternate path to get you to the answer. So this is an example where something was monotonic, it was bounded on one end but not the other end, and it's got to be bounded on both ends for it to converge using this theorem. All right, let's look at one more. And then we're going to play my favorite game in this whole section. So this is kind of like the 2 and 4 sequence, right? It's just going back and forth between 1 and -1. We can see that this guy's bounded, right? It's never going to be below -1. It's never going to be above 1, but it's not monotonic. So therefore it diverges. So this would be another example one. If you try to take the limit of it and show me using the nth limit test, you'd have to like use squeeze theorem or something else to evaluate the limit. You can't evaluate -1 to the n just by itself. We'd have to do some other stuff. But if you listed out the first couple terms and you're like, oh, this thing's bounded, but it's clearly not monotonic, boom, diverges. We're done. Okay, so this is a useful theorem to be able to use when you're doing stuff like this. We could also use the, well, actually we could not. So some of you might try to get clever and use the absolute value theorem, but if you did the absolute value theorem, well, the limit of the absolute value of that would go to 1, and the absolute value theorem only deals with things when they're going to 0. And you also can't use it to prove divergence. You can only use it to prove convergence. Yeah.
You have to know beforehand when something's going to 0 before you can use it. The absolute value.
You can just take the absolute value and see, and if you end up at 0, then you know the other thing went to 0 and you're done. That's why it's worth a try, because it's pretty easy. And actually it makes the limit simpler to do because it's usually taking away the things that were in your way to begin with. Yep. All right, so the last thing in this section that I really enjoy, I think it's super fun, is we've given you sequences where we showed you the pattern, right? And usually we showed you by the nth term, and then you plug in values of n and then generate the list of numbers. But what you need to be able to do is if I give you a list of numbers, can you write the nth term? Can we come up with the pattern? So the reason I've shown you so many different sequences is I want you to see that there's certain patterns that emerge within numbers that we now have ways to mathematically express what was going on. And this will help you a lot when you're looking at sequences because you'll see certain elements within the formula are translating into certain things within the sequence or the series, which we'll get to next. All right, so how do you generate a sub n from a given sequence? So this is something we're actually going to need to do early on in section 9.2. So we need to make sure we can recognize these patterns in these numbers and see what's happening. So the first sequence So what pattern do you see? Anything at all? Just you see something. You don't have to do it all at once, just any attribute you see. It alternates between positive and negative numbers. So if it's alternating between positive and negative numbers, we know we're going to need -1 raised to some stuff, okay? Now what I decide to put in that exponent is going to have to do with what number I want to start counting from. So typically we just default to 1 when we don't know anything else. So if I need the first term to be negative when I plug in 1, then I'm just going to raise this to n. Okay? So that means -1 to the 1 will give me a negative number. -1 squared will give me a positive number. If I had shifted the negative signs to the even terms, well then I probably would have put an n plus 1 in there. So that would have made the odd terms positive and the even terms negative, right? So what else do you guys see going on in there? Do what? The bottom is n factorial. So if we start from 1, we get 1 factorial, 2 factorial, 3 factorial, 4, 5 factorial. So the denominator is n factorial. The numerator's going to be a little tricky. The first two terms look like it might be powers of 2, but then you get to 26, and that kind of shatters that, right? But think about adding 1 to every one of those numbers. What does it turn into? Add 1 to every numerator. It's powers of 3. So 2 is 3 to the 1 minus 1. 8 is 3 squared, which is 9 minus 1, right? 26 is 3 cubed, which is 27 minus 1. So the numerator is 3 to the n minus 1. These are just puzzles and games. All right. So now let's see if we can test this for convergence. Well, it's a good candidate to try the absolute value theorem on because it's alternating. So if I just take the absolute value and check that guy for convergence, then I might be able to show that this whole thing converges. So if I take the limit as n goes to infinity of the absolute value of all this stuff, all that does is take away the -1. And I recognize this limit. This is an exponential over a factorial. So we know the factorial will dominate the exponential, and this limit will be 0. So that means my original sequence also converges to 0. And so it may have been hard to see that those numerators, because if you look at the first several terms of that sequence, the numerators are bigger than the denominators. It's hard to visualize that that's actually going to end up at 0, but if we continued it out, I think after 120 it goes to 720, and you start seeing those factorials just take over the numerator, right? But this would have been hard to kind of tell that. You would have had to list out several terms to really see the denominator taken over, but doing a combination of the absolute value test and then looking at the nth term, we were able to see that that's where it's going to end up. All right, let's look at another one. So what's happening in the numerator? It's powers of 2, right? It's doubling. So if it's doubling, that's probably going to be 2 to the n. And if we check it at n equals 1, we do in fact get 2, and then n squared, and then, or sorry, 2 squared, then 2 cubed, then 2 to the 4th, so that works. All right, what about the denominators? What's happening there? What do you see? Anything. It's cool. They're going up by 2, right? Or they're consecutive odd numbers. Okay? So, right, you got 1, 3, 5, 7. So if we want to write an odd number, we kind of usually go 2 different ways with it. We could say it's 2n plus 1 or 2n minus 1. And so what I'm doing there is I'm saying, well, to get an odd number, you take an even number and you either add 1 to it or you subtract 1 away from it. But we have to figure out which one of these we want to use. So we need our first number to be 1 when n is 1. So if I plug in a 1 here, I'm going to get 3. And if I plug in a 1 here, I'm going to get 1. So I want my denominator to be 2n minus 1. And then you can see, well, when we plug in 2, we'll get 3. When we plug in 3, we'll get 5, right? So it just knocks 1 off every time. So now, if we test this for convergence, and we look at the limit as n goes to infinity, and we apply L'Hopital, the numerator is 2 to the n natural log of 2, and the denominator is just 2, and we can clearly see that exponential is going to grow that to infinity. So this sequence diverges. So we still have a few minutes left of class. This is technically the end of 9-1, right? So we will have a quiz on Wednesday. It'll be in class toward the end of class. And it'll be a group quiz, so you guys will get to work together. I'll post the practice quiz tonight with solutions. You can kind of get an idea of what types of problems, we're going to ask. Please look over it before class because you're not going to have a lot of time to finish the quiz in class. The idea, what you're supposed to be doing in your groups is your strategizing. What do you think you guys are supposed to use? I'm fine after class if you want to work together on it, but it's just due the beginning of the following class period. So we'll start it Wednesday afternoon. If you don't finish it in class, it's fine. You take it home, you bring it back Friday, and turn it in the beginning of class. So what I would like to do, since we need to make sure we stay caught up, is I want to just dip into 9-2 just a little bit. What we're going to do is just get a lot of definitions and stuff out of the way, so when we come back on Wednesday, we can just hit the ground running and start working with some problems. So series is what we're going to spend most of the unit talking about. And the way we relate sequences and series to each other is we said sequences, right, were an ordered list of terms. But series are actually the sum of sequences. So we're going to be adding that list up. So keep in mind that these sequences were infinite. They were infinitely long lists of terms. So that means when you're adding them, you're adding a list of infinitely long numbers. And so if those numbers add up to be a finite sum, right, we say the series converges. If those numbers add up to infinity, then we would say the series diverges. So it's a little bit trippy to see that you can add up a list of infinitely long things and actually arrive at a number. Sometimes we actually can tell you exactly what that value is, all right? So to get kind of our notation down, right, rather than listing the terms from 1 to infinity, we're going to be adding. And so sigma is what we use when we want to add a discrete number of things. And what I mean by that, we're adding individual lists. Where we use integrals when we want to add continuous things, right? Because when you're doing an integral, you're adding all the curve under a line, right? And you need every intermediate value of x. For sequences, they're indexed and you're plugging in discrete values, right? So the length of the list is not discrete, it's infinite, but the values, individual values we're putting on there are. So now, if we have some a sub n term, what we're saying right? It's just keep going forever and ever. We're adding them up. Plus, 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 plus. So there's sort of a tell, right? When you're doing a series, there's one thing you want to always check for before you dive into it and try to check for convergence or divergence. So when you're adding up a list of infinitely many things, you're only going to arrive at a finite sum if the original sequence you were working with converged to 0. And so what we said when a sequence converged to a number is we were saying, well, at some point, every number on this list just becomes that number. So if the sequence converged to 2, you would eventually just get 2, 2, 2, 2, 2, 2, right? If the sequence converged to 0, you would get an infinitely long list of zeros. So if you're adding things together, you want those zeros because every new 0 you add, it just stays itself. So that's how we can actually get an infinitely long list of things to add up to a finite number, because we're just got a bunch of zeros on the back end. So that means that an infinite series will only converge if the sequence converges to 0. And this is so important of a concept, right? One, conceptually, people kind of can usually grasp that idea, like, yeah, if I keep adding 1 or 2 or 3, you know, I'm going to get up to infinity. But what people forget about this is when you kind of get knee deep in all the tests and all the other thing we're going to do, and they forget to check for this. So if you're about to test whether something converges or diverges, and you can look at the nth term and you know the limit is non-zero, you get to shut the whole problem down right then. Because if the sequence itself, right, if the limit of the original sequence is 1, then the series diverges. So if you can identify that nth limit as being non-zero, stop, shut it down, you're done. It diverges because it fails the nth limit test. If the limit is 0, that doesn't mean it converges, it just means now you got to keep going and you actually have a shot at it. Question?
So say you had a infinite series that was essentially 1 and -1 alternating consistently all the way into infinity. Though the sequence would not converge to 0, summing any even group of those would get you 0. So
that sequence diverges
Yes.
because of this rule?
Yes.
And the reason it diverges is because in a minute, we're going to actually talk about partial sums. And when we get to the partial sums, remind me, and I'll show you by using partial sums why that sequence diverges. Because basically, depending on where you stop, you either get 0 or 1, or possibly -1, depending on where we index from. But that is a diverging sequence, and its limit does not go. But this is a hard, fast rule, that if the limit of the original sequence that generated the series does not go to 0, then the series diverges.
Fair enough.
A series cannot converge unless you can go, it sums to this. And you have to be able to take it all the way to infinity. And that's why that one fails, this test. Plus, its sequence doesn't go to 0 either.
Yes, I know the sequence didn't go to 0. The point of it was to present a case possibly where, though a sequence is not going to 0, depending on how you take that sum, you will get 0 as a sum.
Right, and if you're not arriving at one number, then it's a diverging series. Right, because you can't pick your poison, right? The idea is we start from here, we go to infinity, and what do we get, right? So there are ways to sum up things, but we would still call that diverging.
Fair enough.
Because where does infinity stop, right? We can start it anywhere we want to, but where does it stop? And you're right, by pairing odds and evens. But yeah, that's one of the ones, if you take sequences and series, that's one of the ones I like to play around with just to like make your head spin. So let's look at how do we actually test a series for this to sum, okay? So if you want to try to find the sum of an infinite series, we look at the sequence of partial sums. So what we mean when we use that little subscript S sub n is we're saying sum up the first n terms of the sequence. So if we look at, and I'm assuming that our sequence that we're dealing with generally starts from 1. So if you look at S1, well, that's just the sum of the first term, so it's just itself. If you look at S2, well, then you're summing up the first 2 terms, right? S3, we're summing up the first 3 terms. So S sub n is saying sum up the first n terms. So this is why what the game you were playing, if we tried to play it like this, right, you would see that the partial sums alternate between 0 and 1. Or if you index starting from another number, you could make them alternate between -1 and 0. And then you would see what the definition I'm about to give you then, the limit of the partial sums doesn't exist either. So that sequence fails the convergence test like multiple different ways. All right. So what we say is if the sequence of the partial sums converges, to some number s, then the series also converges. And conversely, if the sequence of partial sums diverges, then the series diverges. Yes?
You just say, doesn't this have to be 0?
No, the nth term has to go to 0, but these are going to be partial sums. And I'll show you, we're actually going to look at an example, and you're going to see what these guys look like. All right, so I want to look at my favorite sequence. We're going to now look at the series. This guy. So instead of listing out these terms, we're adding them. Oops. And I actually argue that these are going to add to 1. And we're going to play around with this a lot more later, but I want you to just make a note that this is a form of the geometric series. We're actually going to talk about this quite a lot. But I like to always start with this sequence because one of the things about names, again, we can actually visually show you the convergence of a geometric series using geometry, right? So one of the cool things about this is this particular series. So in football, right, we know that when you have a penalty, there are certain predetermined yards assigned to that penalty, right? Holding's 10 yards, personal foul's 15, right? We have different penalty lengths that are assigned to those things. But if you get too close to the goal line, they change the lengths of those penalties because you don't want to like just walk somebody into the end zone, right? It's not baseball. You can't just walk or run it. So if you get too close to the goal line, what happens to all those penalties? Well, they become half the distance to the goal. So I remember one day my dad calls me and we had just watched some crazy game where we had to vote. It was like literally like 5 penalties in the red zone by this one team, and it was just like half the distance to goal, half the distance to goal. So he was like, well, how many times could you do that, right? Like eventually you're going to run out of room. And I'm like, no, you can do it forever. I was like, that's why we do this. You're literally never going to run out of yardage if you just keep cutting it in half, right? And then, you know, the more they do it, the more you increase the chance of a safety, which is the most humiliating way to get points in football. I love it. All right, so this is what we're doing. There's a reason they pick 1/2, all right? So let's look at how this guy sums to 1. So if I take a square, that's just 1 unit by 1 unit. So the area of this square is 1, right? 1 times 1 gives you 1. And I want to add up all of these fractions. So I'm going to start by taking half the square. And then I want to add that to a fourth. And I get a fourth by just cutting the remaining half in half. And then I want an eighth. So I cut it in half. And then hopefully people can see that this game will keep going on forever. And I'm never going to run out of area. I'm never going to run out of area, and I'm never going to shade anything outside of this box. So we could keep doing this forever. I can just keep cutting every little tiny sliver in half and half and half, and I'll never get to the finish line. And so we can just see pictorially here that by just adding all these fractions, as long as we start at a half and just keep cutting the remaining in half and half, we'll never go beyond 1. We'll never move outside of this box. All right? Another, so this, right, is the same thing. We can think of it as continuously